Right now, as you watch this, a spacecraft built by two space agencies on two different continents is falling toward a planet that almost no one talks about. In 5 months, it will do something only 2 machines in all of human history have ever done. It will arrive at Mercury. And when it gets there, it will look at a world that breaks almost every rule we thought we understood about how planets work. Mercury is the closest planet to the Sun. It is also the smallest true planet in our solar system. If you held Earth in your hand and it were the size of a baseball, Mercury would be a golf ball. Its diameter is 4,879 kilometers, roughly 38% the width of Earth. It is bigger than our moon, but not by much. And it weighs almost nothing by planetary standards. Its entire mass is only 5.5% of what Earth weighs. But do not let the small size fool you, because everything else about this planet is extreme. Mercury's orbit is not a circle. It is a stretched oval, one of the most eccentric orbits of any planet. At its closest, Mercury swoops to within 46 million kilometers of the Sun. At perihelion, the Sun appears more than 3 times wider than it does from Earth. The planet races around the Sun faster than any other world, averaging 47.36 kilometers per second. One full orbit takes just 87.97 Earth days. But here is where Mercury gets strange. While it orbits quickly, it spins incredibly slowly. One full rotation on its axis takes 58.65 Earth days. A single sunrise to sunrise cycle on Mercury, one complete solar day, takes 176 Earth days. That is exactly 2 full Mercury years. So, if you were standing on the surface, you would orbit the Sun twice before the Sun returned to the same position in your sky. This happens because Mercury is locked in what physicists call a 3-to-2 spin-orbit resonance. For every 2 complete trips around the Sun, the planet spins exactly 3 times. Not 2, not 4, exactly 3. And for centuries, scientists got this completely wrong. They assumed Mercury was tidally locked 1-to-1, the same way our moon always shows one face to Earth. That assumption held for decades, until April 1965. That month, 2 radar astronomers named Gordon Pettengill and Rolf Dice pointed the massive Arecibo radio dish in Puerto Rico at Mercury and bounced radar signals off the surface. When the return signals came back, the data was unmistakable. Mercury was rotating once every 59 days, not 88. The textbooks were wrong. Shortly after, an Italian mathematician and engineer named Giuseppe Colombo realized it was almost exactly 2/3 of 88. He proposed that the Sun's gravity, tugging on Mercury's slightly lopsided shape, had locked the planet into this precise 3-to-2 rhythm. He was right, and that same Giuseppe Colombo would later design the gravity assist trajectory that made the first mission to Mercury possible. Because reaching Mercury is extraordinarily difficult. Think about it this way. To fly outward to Mars or Jupiter, you are essentially coasting away from the Sun. Gravity slows you down, but you have momentum on your side. To reach Mercury, you have to fall inward, toward the most powerful gravitational source in the solar system. As you drop toward the Sun, you accelerate enormously. If you do not brake, you will shoot right past Mercury or spiral into the Sun itself. Slowing down requires enormous amounts of fuel or years of intricate gravity assist maneuvers, swinging past other planets to bleed off speed. And once you arrive, your spacecraft must survive temperatures that would melt lead while simultaneously enduring radiation 11 times more intense than anything on Earth. Because of these challenges, only 3 missions have ever visited Mercury in the entire history of space exploration. The first was Mariner 10. NASA launched it on November 3, 1973. Using the gravity assist trajectory that Colombo himself proposed, the spacecraft swung past Venus to bend its course toward Mercury. It flew past the planet 3 times in March 1974, September 1974, and March 1975. It flew past the planet 3 times in March 1974, September 1974, and March 1975. But because its orbital period synced perfectly with Mercury's solar day, the same hemisphere was sunlit every time. Mariner 10 only mapped 45% of the surface. Still, what it found was stunning. A cratered, moon-like landscape, an enormous impact basin called Caloris, 1,550 kilometers across, towering cliffs running for hundreds of kilometers, and something no one expected from a tiny, supposedly dead world, a global magnetic field. Then silence. For 30 years, no one went back. The second mission was Messenger, which stands for Mercury Surface, Space Environment, Geochemistry, and Ranging. NASA launched it on August 3, 2004. It took 6.5 years of gravity assists, 1 past Earth, 2 past Venus, and 3 past Mercury, before it finally entered orbit on March 18, 2011. Messenger became the first spacecraft to orbit Mercury. It mapped the entire surface. It confirmed vast deposits of water ice inside permanently shadowed polar craters. It discovered bizarre geological pits called hollows that appear to be actively forming right now. It found that the magnetic field is strangely offset, shifted northward by 20% of the planet's radius. Messenger operated until April 30, 2015, when it ran out of fuel and was deliberately crashed into the surface. And now, there is BepiColombo, a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency. It launched on October 20, 2018. It has spent nearly 8 years on a winding journey through the inner solar system, executing 1 Earth flyby, 2 Venus flybys, and 6 Mercury flybys. On November 21st of this year, 2026, BepiColombo will fire its engines and enter orbit. It will then split into 2 independent spacecraft. The European Mercury planetary orbiter is designed to map the surface and probe the interior, and the Japanese Mercury magnetospheric orbiter, called MIO, was built to study the magnetic field and the space environment around the planet. Routine science begins in spring 2027. BepiColombo is arriving at a world of contradictions. The surface of Mercury endures the most violent temperature swings of any planet. During the long daytime, equatorial temperatures climb to 427 degrees Celsius. That is 800 degrees Fahrenheit. To melt tin, lead, and zinc. Then, because there is essentially no atmosphere to hold that heat, the temperature crashes during the equally long night. At the poles, nighttime readings plunge to negative 193 degrees Celsius. That is negative 315 degrees Fahrenheit. The total swing from day to night exceeds 600 degrees Celsius. No other planet in our solar system experiences anything close. And yet, Mercury is not even the hottest planet. Venus holds that record because its crushing carbon dioxide atmosphere traps heat so efficiently that the surface stays at a constant 460 degrees Celsius, day and night, poles to equator. Mercury has no such blanket. What it has instead is an exosphere, a layer of gas so thin that the individual atoms almost never touch each other. Surface pressure is less than 10 to the negative 12 bars. That is a vacuum harder than anything most laboratories on Earth can produce. The gases that exist there, hydrogen, helium, oxygen, sodium, potassium, calcium, magnesium, are constantly being ripped from the surface by solar radiation, micrometeorite impacts, and charged particles from the solar wind. They fly upward, linger briefly, and escape into space. The entire exosphere must be continuously replenished, or it would vanish entirely. The sodium in that exosphere does something remarkable. Solar radiation pushes sodium atoms backward, away from the sun, forming an enormous glowing tail. This was predicted in 1986 by the physicist Wing-Huen Ip, and later confirmed and mapped by Drew Potter, Rosemary Killen, Tom Morgan, and Carl Schmidt. Mercury's sodium tail stretches more than 2.5 million kilometers into space. The smallest planet in the solar system has a tail like a comet. Now, let us talk about what is on the surface. The most dramatic feature on Mercury is the Caloris Basin, 1,550 kilometers across, one of the largest impact basins in the entire solar system. Something enormous hit Mercury roughly 3.9 billion years ago, with enough force to excavate a hole wider than the distance from Los Angeles to Dallas. Mariner 10 photographed half of it. Messenger revealed the rest. But the Caloris impact did something else. Directly on the opposite side of the planet, at the exact antipodal point, lies a region of shattered, jumbled, chaotic terrain. Scientists call it the weird terrain. In 1975, geologists Peter Schultz and Donald Galt proposed the explanation. When the Caloris impactor struck, the energy was so tremendous that seismic waves propagated through the entire planet. When those waves converge simultaneously at the exact opposite point, point, they focused their energy like a lens and shattered the crust, thrusting it upward by kilometers. The impact was so powerful that it broke the planet on the far side. In the center of the Caloris Basin itself sits something equally astonishing, a formation called Pantheon Fossae, nicknamed the Spider. More than 200 extensional troughs radiate outward from a central point like the legs of a vast arachnid. Near the center sits a 41-kilometer-wide impact crater called Apollodorus. No one knew this existed until Messenger flew past in 2008. Two competing hypotheses attempt to explain it. Andrew Freed, Thomas Waters, and their colleagues argued in 2009 that as volcanic plains filled the Caloris floor, they placed the crust under immense stress, and the Apollodorus impact triggered catastrophic radial fracturing. James Head and his team proposed instead that the fractures are the surface expression of a massive underground dike swarm, magma pushing upward, doming and cracking the crust, and Apollodorus just happened to land in the center by coincidence. BepiColombo may settle this debate. Now, we go deeper, beneath the surface, into Mercury's iron heart. Mercury is not a normal planet. It is essentially a giant metal ball with a thin shell of rock wrapped around it. The metallic core has a diameter of roughly 4,000 kilometers. The entire planet is only 4,879 kilometers across. That means the core occupies 82 to 85% of the planet's radius. By volume, the core takes up more than half the entire planet. By mass, it accounts for 70% of everything Mercury is. For context, Earth's core is only 16% of its volume. Mars's core is about 25%. Mercury's core is grotesquely oversized. This is why Mercury is so dense. Its bulk density, 5.427 grams per cubic centimeter, is nearly identical to Earth's. But Earth achieves that density because its enormous gravity compresses its interior. If you mathematically remove the compression and compare the raw materials, Mercury's uncompressed density is about 5.3 grams per cubic centimeter. Earth's is only 4.4. Pound for pound, Mercury is made of heavier stuff than any other planet in the solar system. Why? Three major theories compete. The first is the giant impact hypothesis. The second is the evaporation hypothesis. The third is the most recent, magnetic sorting. Whatever created it, that massive core is not frozen solid. In 2007, Jean-Luc Margot and his team used Earth-based radar to measure a subtle rocking motion in Mercury's spin called libration. The amplitude of that wobble was too large for a completely rigid body. The crust and mantle had to be decoupled from something fluid underneath. Mercury's outer core was liquid, and that liquid ocean is doing something extraordinary. It is snowing. Iron snow. As the outer core slowly cools, iron crystallizes into tiny, solid flakes. These flakes are denser than the surrounding liquid, so they sink, falling like snow toward the center. As they descend, lighter sulfur-rich fluid is displaced upward. This creates a constant churning motion, heavy iron sinking, light sulfur rising. Because this fluid is electrically conductive, the churning generates electrical currents. Those currents sustain Mercury's global magnetic field. A tiny planet, keeping its magnetic heart beating through iron snowfall. Now, look at the surface again. Messenger found something there that no one had ever seen on any world. Hollows, shallow, flat-floored, steep-walled, rimless depressions scattered across the planet. They range from tens of meters to several kilometers wide. Their edges are scalloped and razor-sharp. Their interiors are brilliant white with bluish halos. Over 1,500 active hollows have been cataloged. The leading explanation is sublimation. When minerals are exposed to the brutal daytime heat, the volatile component boils directly from solid to gas, escaping into the vacuum. The rock collapses, the hollows grow, Mercury is changing. And then there is the ice. It sounds impossible, but in deep craters at the poles, the sun never rises above the horizon. Rims permanently block the low-angle sunlight, creating permanently shadowed regions where temperatures hover near -173 Celsius. In those perpetual deep freezers, water ice is stable for billions of years. Messenger found it. It is massive, and it is blanketed by a dark layer of complex organic compounds, almost certainly delivered by asteroids and comets. The hottest planet in daylight is preserving water and organic chemistry in its polar darkness. Finally, Mercury is shrinking. As the massive iron core slowly cools and crystallizes, the interior contracts. The rigid crust, unable to shrink smoothly, buckles and snaps, creating immense winding cliffs called lobate scarps. Discovery Rupees stretches 550 kilometers, with up to 1.5 kilometers of vertical relief. Its radius has shrunk by as much as 7 kilometers, and it is still happening. Young, pristine scarps and small grabens prove the faults are still moving. Mercury is still contracting. Right now. 5 months from now, BepiColombo enters orbit around this world, a planet that is simultaneously ancient and active, frozen and burning, dead-looking and alive, a planet where iron snows inside a core that should have frozen solid billions of years ago, where ice and organic chemistry survive in permanent shadow, where the ground is literally collapsing into itself as volatile minerals boil into space, where the entire world is slowly, measurably shrinking. In Part 2, we will go inside BepiColombo itself, the 8-year journey, the thruster failure that nearly ended the mission, the 5 mysteries it was specifically designed to solve, and why what it finds at Mercury could change what we understand about every rocky planet in the universe, including our own. This is just the beginning. On March 29, 1974, a small spacecraft called Mariner 10 dropped to within 704 kilometers of Mercury's surface. On board was a magnetometer, an instrument designed to measure magnetic fields. The scientist responsible for that instrument was Norman Ness, a physicist at NASA's Goddard Space Flight Center. Before the flyby, virtually every planetary scientist on Earth expected the magnetometer to read nothing. Mercury was too small, too old, too cold inside. Whatever molten iron it once had should have frozen solid billions of years ago. A frozen core cannot generate a magnetic field. The instrument was included almost as an afterthought. Then the data came in. Mariner 10 detected a bow shock, a sharp boundary where the solar wind slammed into an invisible barrier and was deflected around the planet. Behind the shock lay a magnetospheric cavity, a bubble of space carved out and protected by a magnetic field that was unmistakably coming from inside Mercury. Ness later described it as one of the most startling sets of data the mission returned. He wrote that the complete body of data favors the preliminary conclusion that Mercury has an intrinsic magnetic field, and that if this is correct, it represents a major scientific discovery in planetary magnetism and will have considerable impact on studies of the origin of the solar system. He was right. 52 years later, we still do not fully understand how Mercury's magnetic field works. And 5 months from now, BepiColombo will attempt to find out. To understand why Mercury's magnetic field is so baffling, you need to understand how planetary magnetic fields are generated. On Earth, the outer core is a churning ocean of liquid iron and nickel. As Earth rotates, this electrically conductive fluid moves in complex convection patterns. Those moving currents of molten metal generate electrical currents, and those electrical currents produce a magnetic field. This is called a dynamo. It is essentially the same principle as an electrical generator, except the generator is the size of a planet and runs on heat escaping from the core. For a dynamo to work, you need 3 things: a large volume of electrically conductive liquid, enough heat flow to drive convection, and rotation to organize the flow into coherent patterns. Earth has all 3. Mercury should not. Mercury's radius is only 2,440 kilometers. Thermal models predicted that a planet this small should have radiated its internal heat into space billions of years ago. The core should be completely solid, no liquid, no convection, no dynamo, no magnetic field, and yet the field exists. It is weak, roughly 300 nanoteslas at the equator, only about 1% of Earth's field strength. But it is there, it is global, it is dipolar, and it is active. So how is this tiny planet keeping its core molten after 4.5 billion years? There are 2 mechanisms, let's explore them. First, Mercury's core is not pure iron. It contains significant amounts of sulfur and possibly silicon. Sulfur acts as an antifreeze. It drastically lowers the melting point of the iron alloy, allowing the outer core to remain liquid at temperatures that would freeze pure iron solid. Second, Mercury's highly eccentric orbit subjects it to intense tidal flexing from the Sun's gravity. Every 88 days, as Mercury swings between 46 million and 70 million kilometers from the Sun, the gravitational stress kneads the interior, injecting thermal energy. There may be a third factor. In 2019, Geeth Manthalake and colleagues published experimental results in the Journal of Geophysical Research showing that an insulating layer of iron sulfide sitting at the top of Mercury's core could act like a lid on a pot. This layer has extremely low thermal conductivity, roughly 4 watts per meter per Kelvin, which would dramatically slow the escape of heat from the core into the mantle. The core stays warm not only because it generates heat, but because it cannot easily lose it. The proof that the core is actually liquid came from Earth-based radar. In 2007, Jean-Luc Margot and his team measured a subtle rocking motion in Mercury's spin, a longitudinal libration. The amplitude was too large for a completely solid planet. The only explanation was that the outer shell, the crust and mantle, was decoupled from the interior by a layer of fluid. Mercury's outer core was molten. Then in 2019, Antonio Genova used MESSENGER's low-altitude gravity data to prove that inside that liquid outer core sits a solid inner core roughly 2,000 kilometers wide. Mercury's interior is layered, just like Earth's. Solid iron at the center, liquid iron sulfur surrounding it, rocky mantle on top, thin crust on the outside. But MESSENGER found something about the magnetic field that nobody predicted, something deeply strange. In 2011, Brian Anderson of the Johns Hopkins Applied Physics Laboratory published data in Science showing that Mercury's magnetic field is not centered on the planet, it is shifted. The magnetic dipole is displaced approximately 480 kilometers northward from the planet's geographic center. That is roughly 20% of the entire planetary radius. Imagine if Earth's magnetic field were centered not at the core, but somewhere under Iceland. The consequences would be enormous. On Mercury, this offset means the northern hemisphere has a much stronger magnetic shield than the south. The southern hemisphere is comparatively exposed, and solar wind particles can reach the surface more easily there. Why would a planet's magnetic field be off-center? The leading explanation involves a process we discussed in Part 1, iron snow. As the outer core cools, pure iron crystallizes out of the sulfur-rich liquid and sinks toward the center. This falling iron snow creates vigorous compositional convection. In 2014, Hautau, Christopher Russell, and their colleagues at UCLA published numerical dynamo simulations in Geophysical Research Letters showing that this iron snow convection can spontaneously break symmetry. In their models, 2 modes of columnar convection overlap. One is symmetric about the equator, the other is not. When they coexist, the magnetic energy concentrates preferentially in one hemisphere. The result is a dipole field that appears to originate from a point shifted away from the center. The iron snow is not falling evenly, the dynamo is not symmetric, and the magnetic field reflects that asymmetry. Johannes Wicht and Daniel Hayner, publishing detailed reviews in 2017, showed that a stably stratified layer at the top of the core, where sulfur concentration increases with depth, could further enhance this asymmetric dynamo behavior. The field we see at the surface is not just generated by the core, it is filtered and distorted by the layers above it. Now, Mercury sits closer to the Sun than any other planet, and its magnetic field is roughly 100 times weaker than Earth's. This means its magnetosphere, the protective magnetic bubble, is tiny. Earth's magnetosphere extends tens of thousands of kilometers on the day side. Mercury's stands off the solar wind at an altitude of only 1,000 to 2,000 kilometers. The solar wind at Mercury's orbit is ferocious. The magnetic pressure that squeezes Mercury's magnetosphere is vastly greater than what Earth experiences. James Slavin at the University of Michigan has spent years studying what happens inside this compressed magnetic cage. Using MESSENGER data, he documented showers of flux transfer events at the dayside magnetopause, moments where the solar wind's magnetic field connects directly with Mercury's field and rips magnetic flux away, dragging it to the nightside tail. On Earth, this process, called the Dungy cycle, takes 1 to 3 hours to complete. On Mercury, Slavin showed it takes 2 to 3 minutes. The entire magnetosphere loads with solar wind energy and then explosively releases it in a substorm 60 times faster than at Earth. The entire magnetosphere loads with solar wind energy and then explosively releases it in a substorm 60 times faster than at Earth. This is exactly why BepiColombo was designed with 2 spacecraft. Messenger was a single probe. When it measured a magnetic fluctuation, scientists could not tell whether the spacecraft had moved into a different region of the magnetosphere or whether the entire magnetosphere had changed around it. This is called spatial temporal ambiguity, and it is the fundamental limitation of any single-point measurement. BepiColombo solves this by separating into two independent orbiters. The Mercury planetary orbiter, built by ESA, will fly in a tight polar orbit at 480 by 1500 kilometers. It carries a sensitive magnetometer to map the intrinsic field generated by the core. Meanwhile, the Mercury magnetospheric orbiter, called MEO, built by JAXA, will fly in a highly elliptical orbit at 590 by 11,640 kilometers. MEO will monitor the incoming solar wind, measure the magnetospheric boundaries, and track the rapid reconnection events and substorms. With both spacecraft operating simultaneously, scientists can subtract the external solar wind noise detected by MEO from the surface-level data collected by MPO. What remains is a pristine, uncontaminated mathematical portrait of Mercury's internal dynamo. For the first time, we will be able to see the core's magnetic signature without the sun's interference obscuring it. But the magnetic field is only one of 5 major questions BepiColombo was designed to answer. The second is about Mercury's surface. Mercury is strangely dark. Its bond albedo, the total fraction of sunlight reflected in all directions, is only 0.088. That is less than the Moon. Mercury reflects roughly 2/3 as much light as the lunar surface. For decades, no one could explain why. Then Messenger found carbon, lots of it, spatially correlated with the darkest terrains on Mercury, regions called low reflectance material. In 2015, Kathleen Vander Kayden and Francis McCubbin, working at the University of New Mexico, published an elegant explanation. Mercury formed under extraordinarily reducing conditions, meaning almost no oxygen was available. Under these conditions, typical silicate minerals were denser than the surrounding magma and sank. But graphite, a crystalline form of carbon, was buoyant. As Mercury's primordial magma ocean cooled, graphite floated to the top, forming an exotic primary crust made entirely of carbon. Over 4.5 billion years, meteorite impacts and volcanic eruptions mixed this graphite into the silicate crust that eventually covered it, darkening the entire planet. BepiColombo's MERTIS instrument, a thermal infrared spectrometer built by the German Aerospace Center and the University of Münster, operates in wavelengths between 7 and 40 micrometers. These wavelengths are exquisitely sensitive to the molecular bonds in minerals. MERTIS will provide the first definitive spectral identification of graphite, calcium sulfide, and magnesium sulfide in the low reflectance material. Messenger's spectrometers could see that Mercury was dark and carbon-rich. BepiColombo will tell us exactly what molecules are responsible. The third question concerns where Mercury formed. Before Messenger, every theory for Mercury's oversized iron core involved extreme heat, a giant impact that stripped the mantle, solar radiation that boiled the rocks away. Both scenarios demand that Mercury should be severely depleted in volatile elements, the lightweight atoms that evaporate easily under heat. Scientists test this by measuring the ratio of potassium to thorium. Potassium is volatile. It boils off at moderate temperatures. Thorium is refractory. It survives extreme heat. If Mercury endured a catastrophic heating event, its potassium should be almost gone while its thorium remains, producing a very low potassium to thorium ratio. Messenger's gamma-ray spectrometer measured a ratio of approximately 5200. That is comparable to Mars and Earth. It is more than 14 times higher than the Moon's ratio of 360. Mercury retained its volatiles. It was never globally superheated. This led Brad Hansen, publishing in the Astrophysical Journal in 2009, to propose that Mercury may not have formed where it is now. In dynamical simulations built on the Grand Tack model, where Jupiter migrated inward early in solar system history, the terrestrial planets formed from a narrow annulus of material much closer together than their current orbits. Mercury could have assembled near the modern orbits of Earth or Mars in volatile-rich territory before gravitational interactions with the growing proto-Earth and Venus flung it inward to its current sun-scorched position. BepiColombo's MIXS X-ray spectrometer and MGNS gamma-ray and neutron spectrometer will generate ultra-high-resolution global maps of potassium, thorium, and other key elements. By mapping exact geochemical gradients across the surface, scientists can trace the original nebular material that built Mercury and determine whether it matches the composition expected from the inner solar system or from farther out. The fourth question is whether the hollows are still changing. As we covered in Part 1, hollows are shallow, bright, rimless depressions formed by the sublimation of volatile sulfide minerals. They appear geologically young. BepiColombo's Symbio-SYS camera suite will rephotograph the exact hollows MESSENGER imaged more than a decade ago at resolutions down to 6 meters per pixel. If the hollows have expanded, deepened, or if new ones have appeared, it will prove that Mercury's surface is actively evolving right now. The fifth question is the ice. MESSENGER confirmed water ice in permanently shadowed polar craters using neutron spectrometry and laser altimetry. But it never directly measured the ice's composition at the molecular level. BepiColombo's MGNS will map subsurface hydrogen concentrations with higher precision, while MERTIS will measure exact temperatures inside the shadowed craters to verify long-term ice stability. The combination will tell us not just that ice is there, but how much, how deep, and whether the thermal environment can sustain it for billions of years. Now let me tell you about the journey that brought BepiColombo to the threshold of Mercury's orbit. The mission is named after Giuseppe Colombo, the Italian mathematician who proved Mercury's 3-to-2 spin-orbit resonance and invented the gravity assist technique that made Mariner 10's triple flyby possible. He lived from 1920 to 1984. He was a professor at the University of Padua. Without his mathematics, no spacecraft would have ever reached Mercury. BepiColombo launched at 1:45 UTC on October 20, 2018, atop an Ariane 5 rocket from Kourou, French Guiana. The total mission cost is approximately 1.65 billion euros, making it one of the most significant investments in planetary science history. The mission is led by Johannes Benkoff, who served as ESA project scientist through the early mission phases, with Geraint Jones now holding that title, and Go Murakami as JAXA project scientist. Santa Martinez San Martin serves as ESA mission manager. The 8-year cruise to Mercury required 9 gravity assist flybys, 1 past Earth in April 2020, 2 past Venus in October 2020 and August 2021, and 6 past Mercury itself in October 2021, June 2022, June 2023, September 2024, December 2024, and January 2025. Each flyby bled off orbital energy, gradually lowering the spacecraft's velocity so it could match Mercury's orbit. The closest approach was the 4th Mercury flyby, which brought BepiColombo to just 165 kilometers above the surface. That 4th flyby was not supposed to be that close, and the reason is the crisis that nearly killed the mission. In April 2024, engineers discovered a power anomaly in the Mercury transfer module's solar electric propulsion system. Unexpected electrical currents were flowing between the solar arrays and the power distribution unit. The electric ion thrusters could no longer operate at full capacity. They were permanently limited to roughly 90% of their required thrust. That may sound like a small margin, but in orbital mechanics, margins are everything. The spacecraft could no longer brake hard enough to reach Mercury by its original arrival date of December 2025. Santa Martinez. San Martin described the severity of the situation when she stated that following months of investigations, the team had concluded that the thrusters would remain operating below the minimum thrust required for orbit insertion in December 2025. The flight dynamics team at ESA did not give up. They recalculated the entire remaining trajectory from scratch. They found a new path that required less thrust but took longer, delaying arrival by 11 months. They adjusted the fourth Mercury flyby geometry, bringing the spacecraft 35 kilometers closer to the planet than originally planned, down to 165 kilometers to squeeze out additional velocity reduction from gravity alone. They saved a multi-billion euro mission through mathematics. The orbit insertion sequence begins in September 2026, when the Mercury transfer module, having completed its electric propulsion role, is jettisoned. The spacecraft does not use electric propulsion to enter orbit. Instead, it relies on a weak stability boundary approach, allowing Mercury's gravity to gently capture the spacecraft. The Mercury Planetary Orbiter's chemical propulsion system, equipped with 422 Newton bipropellant thrusters, then executes a series of braking burns to secure the orbit. On November 21, 2026, BepiColombo enters Mercury orbit. In December, the two orbiters separate. MEO is released first, spun up to 15 revolutions per minute for thermal stability, and placed into its elliptical science orbit at 590 by 11,640 kilometers, with a 9.3-hour orbital period. The protective sunshield structure is then jettisoned. Finally, MPO fires its thrusters to lower its orbit to 480 by 1,500 kilometers, with a 2.3-hour period. Both orbits are polar, inclined at 90 degrees. Nominal science operations begin in April 2027 and run through May 2028. A one-year extension is planned through May 2029. So why does any of this matter beyond Mercury? Because Mercury is not just a planet, it is a laboratory. In our entire solar system, only 3 solid bodies generate active internal magnetic fields through a dynamo: Earth, Mercury, and Jupiter's moon Ganymede. Mercury's dynamo operates under conditions that should not work. The core is small, the rotation is slow, 59 Earth days per spin, the thermal stratification is stable, and yet the field exists. Understanding how Mercury's dynamo survives at the absolute edge of what physics allows teaches us about magnetic fields on rocky exoplanets orbiting close to their stars, worlds we can detect but never visit. Mercury's oversized iron core makes it the closest local analog to a class of exoplanets called hot super-Earths and lava worlds. In 2018, Alexandre Santerne and colleagues published the discovery of K2-229b in Nature Astronomy, a planet with a Mercury-like composition orbiting scorchingly close to its star. To interpret planets like K2-229b and 55 Cancri e, astronomers use Mercury as their baseline template. What BepiColombo learns about how Mercury's core formed, how its mantle was lost or sorted, and how its chemistry survived will directly inform models of worlds orbiting other stars across the galaxy. Mercury also preserves a record that no other inner planet can offer. Earth's surface is constantly recycled by plate tectonics. Venus's surface was globally resurfaced by volcanic eruptions roughly 500 million years ago. But Mercury has no plate tectonics. It has no thick atmosphere to erode its features. Its cratered surface is a 4.6 billion-year-old time capsule, preserving an immaculate record of the late heavy bombardment and the impact history of the early inner solar system. Every crater on Mercury is a data point in the chronological timeline of our cosmic neighborhood, and the planetary science community is already looking beyond BepiColombo. In the 2020 Planetary Mission Concept Study for the Decadal Survey, scientists including Paul Barn and Kathleen van der Kaden detailed a New Frontiers-class Mercury lander proposal. The concept calls for a spacecraft that would land on the surface and survive for 88 Earth days, one full Mercury night, powered by a next-generation radioisotope thermoelectric generator. It would directly analyze surface geochemistry, measuring the minerals and volatiles that Messenger and BepiColombo can only study from orbit. A lander is viewed as the necessary precursor to the ultimate goal, bringing a piece of Mercury home, a sample return. But that future begins with what happens in 5 months. When Norman Ness pointed his magnetometer at Mercury in 1974, the scientific community expected to find a dead rock. They found a world with a beating magnetic heart. When Messenger arrived 37 years later, scientists expected a barren lunar twin. They found ice, organics, active geology, an off-center magnetic field, and a chemical composition that defied every formation model. Now BepiColombo arrives with 2 spacecraft, 16 instruments, decades of accumulated questions, and the mathematical legacy of the man it was named after. Jack Wright, an ESA research fellow and planetary scientist, captured the stakes when he said that Mercury's heavily cratered surface records a 4.6 billion-year history of asteroid and comet bombardment, which, together with unique tectonic and volcanic curiosities, will help scientists unlock the secrets of the planet's place in solar system evolution. David Rothery added that it will clearly be of interest for BepiColombo scientists because Mercury has excavated dark, low reflectance material that may be remnants of its early carbon-rich crust. And Geraint Jones, BepiColombo's current project scientist at ESA, said in January 2025, "We cannot wait to see what BepiColombo will reveal. While we are still 2 years away from the mission's main science phase, we expect this encounter to provide us with beautiful images and important scientific insights into the least explored terrestrial planet." The least explored terrestrial planet. That label will not last much longer. Mercury is arguably the most underrated world in the solar system. It is small, battered, and sunburned. It sits in a region of space so hostile that only 3 machines have ever gone there. But beneath that scarred exterior lies a planet that defies every expectation. An impossibly large iron core kept molten by sulfur antifreeze and insulated by an iron sulfide lid. A magnetic field shifted 480 kilometers off-center by snow made of iron falling through a liquid metal sea. A primordial graphite crust from a time when the entire planet was an ocean of magma, water ice, and organic molecules preserved in permanent polar darkness on the most irradiated surface in the solar system. A crust that is still buckling and cracking as the planet slowly, measurably shrinks. Mercury forces us to abandon the assumption that small means simple, that close to the sun means well understood, that old means dead. In 5 months, 2 spacecraft will separate above this world and begin the most detailed study of any planet other than Earth and Mars. What they find will reshape our understanding, not just of Mercury, but of how rocky planets form, how magnetic fields survive, and how the chemistry of life gets distributed across a solar system. The smallest planet has the biggest secrets, and we are about to open them.